Hi, everyone. Welcome to May Tech Talk. Here's a little bit about me. I've been with GE since about 2014. Worked for various different utilities and protection and controls engineer. Today we're going to talk about arc flash, a little bit about what is arc flash. We've seen a lot of presentations about that, and then we're going to talk about some mitigation methods, particularly zone interlock and bus differential, and sort of tie it together with a little bit of centralized protection at the end. So the first thing, what is arc flash? So arc flash is basically a flashover between two conductors, or a conductor and ground. We got a fault, big fault. Current's going to pass through there, ionize the air, and continue to grow. This arc has a lot of energy, and it's a function of the system voltage, available fault current, how long the fault's present, and the material that's there to feed the fault. These happen quite often, and they're very intense. That intensity is something pretty amazing. So we can get up to about 20,000 degrees C, which is hotter than the surface of the sun. There's projectile producing pressure. There's a huge pressure wave, toxic vapors, and intense sound. This is a major event. I'm sure you've all seen videos online or in safety presentations of arc flashes. So it's a pretty powerful event. In that light spectrum, it's not super unique. It's pretty wide, 300, 800 nanometers, and the intensities vary. But the arc will continue to grow if it's not controlled. And a single phase to ground fault can grow and involve other phases. Typical causes of the arc flash are things like dropping tools. So if you're working in an energized cabinet, drop a tool, makes contact between the conductor and ground, or two conductors, you get a flash. Bad news. Go to arc discharge. We have a lot of old equipment in the electrical system. We can start having corrosion growing on conductors, breaks down the airspace we have for insulation, grow to an arc. For workmanship, improper procedure, loose connections. That's a bigger one than you think. I was doing commissioning in a live substation. This particular circuit was energized, but I went to go check a CT circuit, and the ring lugs weren't crimped. The wire was just in the sleeve. Missed crimping it altogether. So you can have loose connections that can grow and cause these arcs. Environmental conditions, pollution in your environment, you could have gases and stuff like that that can be present, contamination that's blowing around, creating an arc. Substandard equipment, improper design. We all have these temporary solutions when we're doing work. We jerry-rig stuff just to try to get our testing done, and these temporary installations can have problems because they're not designed to our permanent standard. So that can be a big issue. I've seen some temporary conditions that had tags on them from 1979. So sometimes temporary lasts a while, but that's not a good thing. Risk of rodents. Vermin gets in there. That's always an issue in switchgear. Some kind of critter getting in there and creating an arc. Bad news for them, bad news for you if you're near it when it happens. The arc flash energy profile. So as I said earlier, this thing is a function of time, and so the energy grows exponentially. So as soon as the arc flash happens, we get a lot of light, we get pressure, and then we get heat. And the longer that the arc is present, the more energy that gets dissipated. So ideally, we want to sense this and clear it as quickly as possible. You can see on the slide here in that purple area that's 0 to about 90 milliseconds, and we're going to have scattering objects, switchgear damage, ear and body damage. There's just no real way to avoid all that because time is a function here. We can detect quickly, but then we have to clear it, and that's going to require the circuit breakers to open up and clear the energy, break that source of energy for the fault. So all these things take time. So we can try to eat up a little bit of time on our protective relays. That's where we have the most control. Talk about some mitigation techniques. So typically when we do our design, we try to do a design for reliability. And we have this hierarchy of hazard control measures. And so up at the top, these have the most effectiveness. Down towards the bottom, they have the least. So ideally, we'd like to eliminate the hazard altogether. We don't have to worry about anything. That's going to be of the most effectiveness. If we can't do that, then we can try to substitute less hazardous materials. Go as far as we can with that. Engineering control, reduce risk. We can engineer things to offer this type of protection. We do warnings and signs. Stand back, stay away, be careful. Those are effective as the people obeying the signs. Administrative control, so we have procedures on how we work with stuff like that. So step-by-step procedures, do this, do this, do this. Again, we have a lot of humans involved with that, so steps can be missed, not 100% effective. And lastly on that list is PPE, so personal protective equipment. That's a last-ditch resort that we have to offer protection for our personnel. Where if we can eliminate the risk, we're going to sort of focus in these two areas here, trying to design our equipment to handle that short circuit, proper interlocks. We want to have some ways to prevent people from getting in situations where they're energized. Ideally, we can work in a de-energized cabinet, but if we can't, we want to try to put as many safety factors as we can in place. Fast protection, we'll be talking about here a little bit later. That's going to offer us our engineering controls where we can detect a fault and then call for a clearing of the fault as quickly as possible. We can do things with arc-resistant switchgear, so if we do have something, we redirect that energy in another direction away from our personnel. Proper grounding to help us detect these abnormalities as they occur. Several strategies that we can implement here to look at to address the arc flash. It can be active or passive. An example of the active protection would be the bus differential relay. We're monitoring continuously for an abnormality, and then we're going to operate and clear that. Passive is going to be something like arc-resistant switchgear. So if we do have it, we're going to redirect that energy out of the way. Children or personnel, we're going to minimize the event. Equipment damage. Preventative maintenance is always a big thing. Talked about earlier about contamination, so keeping things clean. Doing infrared scanning, looking for any kind of hot spots that are building up. Operate equipment remotely. So if we can do things where we remove personnel from in front of a danger zone, that works great. That reduces exposure and minimizing the incident energy. So we want to clear that fault as quickly as possible so we're not riding up on that exponential energy curve. So this minimizing the incident energy. This graph over here shows the kind of we showed on that exponential curve where the longer the fault's there, the more energy that's available. So appropriate grounding so we can detect these things. Attempting to reduce short circuit availability. Reducing total fault clearing time. So as I mentioned before, we have some control there with the relaying that we choose. Certain relaying will detect and operate faster than other types of protection. And then we have the circuit breakers that are clearing. That's going to be the biggest chunk of time that we have in this whole equation here, because the circuit breaker is going to be in the 3 to 5 of a cycle range. Our relays, we can start being in the 1 to 2 cycle range. So that's where we can sort of try to eat up a little bit of that time and bring that down. But the circuit breakers are going to be where the majority of the clearing time lies. So that's just applying protective relays, arc flash protection relays. So light sensing relays are another option. All right, so here's a couple of the different relays approaches that are available. Zone selective interlock relays. So these are nice. It's simple to add this to an existing system, potentially, because it uses your main bus relay plus your feeder relays. You're going to need to be able to have these guys communicate with each other. So that's where the additional complexity comes from. Bus bar differential protection, this is nice, it's fast. The cool thing with this is it's unit protection, so there's no coordination required between anything. Depending on how your switch gear's laid out, the cabling may be somewhat of an issue. Light sensors look for that initial light. They can see that light and operate quickly. Downside is that they can have false stripping if they're not supervised by anything. So we can supervise them with an overcurrent element. That makes them more secure, but there are additional sensors, so sometimes they are hard to place. The fiber optic cable is fragile. These installations where they get broken because they're secured down too tightly. So it's a fragile piece of protection as opposed to using a differential. We're using the CTs, which are very robust. Last one listed there is a light and pressure sensor. That's a nice concept because it doesn't require overcurrent, but it doesn't work well with air blast breakers, and it's very, very hard to test. Makes it non-desirable. So what we have right, for the most part, is overcurrent protection. And so this diagram just shows our typical overcurrent coordination characteristics over here. We have breaker 52-1 near bus 1 and a breaker 52-2 near bus 2. We have a stacker curves and we get some kind of coordination time between them, so we give backup protection because we always want to have overlapping protection in our designs. The problem is, if you look and see that on your screen there, the faulted F3, which is to the right of 52-2, the bus 2, if we have a faulted F3 or a faulted F2, which is to the left of bus 2, the relaying over at bus 1, those are going to look pretty identical. So we're going to have long clearing time for those because we have to coordinate with the relay at bus 2. So if we have anything between bus 1 and bus 2, we're going to have a long clearing time. Now, ways to overcome this would be to use like a maintenance switch. So when we go into maintenance mode, we're going to be working in the cubicle into that bus. We switch to a maintenance mode. We take the overcurrent curve at 52-1 and we shift it over so it operates a lot quicker and we don't worry about coordination. This gives us some faster clearing, but it does have a human aspect on there, and it is possible to miss putting it back into normal operation mode, and then you leave the substation, you have a fault, you miscoordinate, and you trip out more than you'd like. But it is an option. One of the biggest problems comes from the CT. So we use the CT to know what's going on in the system. The CT is going to give us a representation of the amount of current that's flowing on the different feeders and into the bus. We need this for our protection to operate quickly. Problem is, if we have a high enough magnitude fault, the CT can saturate and then it will not accurately reproduce the current that's actually present. This causes an issue when we start doing differential type protection. So one thing that we can do with our existing type schemes that I mentioned earlier was a zone selective interlock. So with this scheme here, we have our typical layout where we have our main breaker, feeder breakers. Instead of just having the time over current curves coordinated, we use an instantaneous element on the main breaker that is supervised by the feeder breakers. So what goes on over here is if there is a fault on one of the feeders, the main breaker would see it, but so would the feeder breaker. The feeder breaker will send a signal to the main breaker telling him, I got this, and the main breaker will restrain. If there's a fault on the bus, the main breaker will see this fault, the feeder breakers won't. The main breaker does not get any kind of signal from the feeder breakers, and he trips higher speed. So this is not quite instantaneous. We need to have a little bit of a coordination time because we need time for that message from the feeder breaker to get to the main breaker. This is if you have a network solution like shown here where you can pass GOOSE messages, this works out really ideal because GOOSE messages are super fast. You can get that message there in around 3 milliseconds. If you don't have GOOSE messaging, you can do it with contact I/O, but you will gain additional time because now you have the contact output operate time and then the main breaker relay or the main relay sense time. Now you're looking probably 6 to 8 milliseconds as opposed to 3. So there's additional time if you're using contact I/O as opposed to using something like GOOSE messaging. This is kind of limited to simple main and feeder breakers, the distribution type buses. Next option we might think about is, well, let's do an overcurrent differential relay using an overcurrent relay. Well, we can do that. We can take all the CTs and we can parallel them up, take them into a relay, and again, we have some of the current should equal 0 for no fault, and if there's an internal fault, we should get something other than 0. Issues with something like this is all the CTs are going to have the same ratio, because we're just summing up the currents. And if we do have saturation, we need a way to account for that. So we're going to have to use time. We're going to use a time overcurrent function in that relay, and give ourselves a little bit of time for the feeder breaker to clear its fault on the saturated CT. Not super fast, so not really ideal for arc flash mitigation. High-impedance bus protection. High-impedance bus protection is fast and reliable bus protection. The protection kind of relies on the fact that you're going to have saturation. So the saturated CT improves your security, as all the fault current has, the saturated CT has a lower impedance than the high impedance in the relay, so that current flows through that way. An internal bus fault will flow into the relay and create a large voltage, and the relay operates. So it's a very fast and secure type of protection. The drawback on something like this is that all the CTs need to be identical, and they need to be dedicated. So you can't use them for anything else. And in switchgear applications, this is not really feasible because you don't have a lot of space to have an extra set of CTs for every feeder in the main. Other things that you want to take into consideration is keeping the lead lengths equal from the CT to the relay. This is highly impedance dependent. So, what's our other options? A low impedance bus differential. So the low impedance bus differential sort of incorporates the best of all of these worlds over here. It's fast, it's fairly easy to implement. The CTs can be different ratios, it can be different classes. The CTs can be used for other elements. So if you have a feeder protection relay, that CT can share that in both relays without an issue. It's secure. We don't have the same type of security that the high impedance does, in that it's relying on the CT to saturate for the relay to work properly. It's measuring that, but it does have CT saturation detection, which increases security and a directional element. So this works kind of like we talked about with the differential with the 51, where we just sum of the currents equals 0. So can't go wrong with Kirchhoff. Take all the main, all the feeders, add them up, they should equal to 0. To improve the security, we're going to introduce a restraint quantity. That restraint quantity can be calculated in various different ways. The way that we do it is we pick the maximum of each of the individual contributors. So this shows here the max of absolute value of I1, I2 through IN. Another set of the equations over there. Sum of the currents, pretty simple. How does this actually work? So we have this diagram over here, simple circuit, 4 elements going into this bus, C1, T2, C3, and C4. The relay uses per unit to calculate this, so we normalize everything. Since it's in per unit, we need a base quantity. The relay will use the maximum CT ratio from each of the inputs. So in this case, it's 1,000 of 5, so 1,000 is our base quantity. It'll turn everything into per unit, so C1 becomes 0.07 per unit, C2 0.24 per unit, C3 0.19 per unit, and C4 is negative 0.5 per unit because it's leaving the bus. So when we add these currents together, we get a differential current of 0. So Kirchhoff's current law satisfied, 0. We have a restraint quantity of 0.5 per unit, which is the maximum of any of the individual contributors. Now the way we use this is with the dual slope characteristic. So we have 2 different areas on this curve. We have the low region, which is for smaller currents, where saturation is harder to detect. It is possible, because you can have DC offset and some residual flux, so we need to implement some additional securities. In the high region, this is where we're looking for larger currents. Saturation is highly possible, but it's easier to detect. So we're only going to need to get security if we detect that there is saturation. The way that the dual slope overcomes these CT errors is slope 1 handles these small errors in CTs. CTs aren't perfect, they're not identical between all of them, so you will have some sort of differential current even when there isn't any, just because of the nature of the CT. But that first slope takes care of that. You'll be below the pickup and be blocked. A large area, when we get saturation, we need to increase our restraint area, and slope 2 accommodates that. For security, we have a phase comparison element, and this is going to detect internal versus external faults. So one thing that happens is for an internal fault, all the currents are going into the bus. They're all going to be in the same direction. So we have a 90-degree window that says if all the current phasors are within this 90-degree window, we have an internal fault. So we set our direction flag as 1. If one or more of the current vectors is out of that 90-degree window, we set our direction flag as 0, saying that the fault is external. The way this looks within the logic is for a fault that goes where that red star is, we would have differential current, which would satisfy this, and then we're going to look at direction. So we're going to look at the direction flag and make sure that all of the currents are in that 90-degree window. If that's satisfied, this AND gate's satisfied, what is OR gate, and we have a % differential operation. If the direction flag is not satisfied, then we will restrain. Something to take into consideration here when you're doing testing is that with just putting 2 restraints, very difficult to try to get, it's nearly impossible to get these currents to come within that 90-degree window and give you your operation right on the curve. So if you're doing testing, you can monitor this flex operand to verify the shape of the curve. The time difference is restrained differential currents. So for an internal fault, on the slope 1, we're going to just jump into here into the tripping region, verify the direction, trip, fault's cleared. For an external fault, we're going to go from T0 to T1. We're still in the restrained region. If the CT saturates, now it's not giving us an accurate reproduction of the current that's on that feeder. It jumps up over here at T2. Well, now we're in the trip region, but we don't want to trip because this is an external fault. So the relay notices that there was saturation going from T1 to T2, inserts its saturation detector, and now we have to look for direction. the direction element would not be satisfied because it's an external fault, and we would properly restrain. This shows it in the logic over here. The reason this works is because flux cannot change instantaneously. So the CT cannot saturate instantaneously. The relay notices that we're going from a restraint characteristic to a trip characteristic, and can assess that the CT has saturated. It will assert the saturation flag that's highlighted over here, and now it forces the relay to go through its direction element. So the graph to the left over here, the red star shows for high magnitude internal fault with no saturation, we would go right into the tripping area, and we would be able to trip high speed. For an external fault, which is what the blue star and line show, we would travel along the x-axis and then jump up on the y-axis very abruptly. So this gets flagged as saturation, and we're forced to look for direction. It gives us our additional security. For low impedance bus differentials, they typically do offer a unbiased operation. You need to be careful in setting that one because there is no bias. It's looking at strictly the differential current. So it could be fooled by this. So you need to set that one appropriately. Setting it too sensitive does not buy you additional protection. It actually makes you less secure. So when setting these, have caution in that respect. That sort of covers the differential aspect on how the low impedance differential can be used to securely protect your bus and offer you high-speed protection for arc flash. The low impedance bus differential can also provide backup protection to your feeders. Going along that line, I want to talk about centralized protection. Centralized protection is another option that's available, and what we do here, as opposed to having individual relays at each feeder and then a separate bus differential relay, we have one relay, and then we have, in this is showing merging units at the different feeders. So at each CT, we bring in CT information, we can bring in breaker status, we can bring in alarm contacts. All that gets fed back to a central relay, which would provide you with your bus protection, as well as your individual feeder protection, which would be your overcurrent protection, your recoils, including sync check. So all that can be accomplished with one relay. We can add a second relay and offer redundancy, which is something we typically don't have in lower voltage systems. Now we'd have a redundant system that is offset. So the relay itself can provide you control. You can operate breakers. You're away from the breaker. You're not doing anything in front of the breaker, so that increases personnel safety that way. So when they operate the breaker, then it's standing in front of the cubicle. Other nice thing is, since these merging units are bringing back everything via fiber, there is no possibility for open CTs. So additional safety is added by doing this. You can do something like this with traditional relays and CTs. The drawback is that you're bringing back a lot of copper cable to the cubicles, and that can be difficult to bring back each of the CTs to a central location, strip and close to do the individual breakers and aux status. So there's a lot of additional copper wire that's being run. This one here, the merging units live in the cubicle, and we're just bringing back small armored fiber back to the relay. This centralized relay over here provides you a lot of information now. So from this central location, you can set up one lines of your station, you can do operation, you can get metering, you can set up alarms, annunciators, panels, all your sequence of events for your entire switchgear. all available in one location. You want to bring this back to a remote location, you're just connecting to one device, or two if you have the redundancy. Bring back that information. So it can simplify your substation design, allowing for a lot of consistency as well. One of the nice things about this that I like is it really allows for the cookie cutter design. I know with a lot of projects going on in most companies, it's very difficult to keep up with everything. So this solution allows for a super standardized design that gives you a lot of flexibility. The merging units can be all wired identically with the CTs, VTs, breaker status, any alarms. They can do trip and close and lockout functions all within there. So all that gets wired in the cubicle, and all you're bringing back to the relay is a fiber. That information then is from every cubicle is available to your protective relay, so that you can do any type of specialized control functions that you need to do. Load shed, trips, recloses. I mean, the possibilities are pretty much endless because now you have all the information available to your relay. But the nice thing is that it's all standardized. You can not use that information if you don't need it, or it's available if you do. And on the application, it's only a matter of software to configure that and say, okay, now I'm using this and have that signal available, I'm going to use it. So a lot of flexibility. I've done some stuff where you needed to add in something like recloser cutoff status to an adjacent breaker. That was not a big thing. You got to add in some wire from a contact output of one relay into an input of the other. Simple enough, except that the construction crew had left. And so we're trying to scramble to find wire to wire this in. If we had something like this where the information was available over a network, then with a matter of programming, you could have that signal in there and been done and added that in. With this type of scheme, like I said, it's a very cookie cutter scheme. So from one position to every position, every cubicle, every bay, all wired exactly. My screen cleared for a sec, sorry. Everything's identical. So it really does allow for this cookie cutter design. The options that we have available for sizing, you can do a direct connection, so no switch networks. We can handle up to 8 merging units. If you need more than 8 merging units, we can go into a switch network, which can take you up into larger numbers. For a bus protection, we can go up to 24 circuits. So lots and lots of possibilities. The network design for large ones continues along this cookie cutter approach where every layout is identical. So all the merging units are tied together the same way to the switch. That switch goes off to your station. That information is available to all the relays in the station if you have multiple relays. If you have just one, that information is available to that one relay. You can do all your protection functions and ultimately simplify your design, making a quickly repeatable and reliable system. All right. So, in the conclusion over here, we talked a little bit about arc flash. It's a serious concern. So we have things like light sensors that can be done. Some issues with that. Bus differential protection provides reliable protection. It's consistent and it's fast. Carrying along that line, we can do the option of centralized protection, which can help simplify protection schemes while adding additional protection functions. So there's a lot of possibilities for us out there. Okay, let me scan through these here. Okay, so the first question I see here, it says, does the multi-lane 850 work with this design? So The multi-lane 850 will work with the zone interlock scheme. It does not work with the centralized protection scheme. For the centralized protection scheme, this would be the UR. So the question here says, in terms of arc flash protection, is it so that zone selective interlocking or differential protection, bus protection is kind of outdated nowadays, as there are several technologies available based on light and overcurrent detection, which is more reliable and faster? So there is light sensors. I think there's issues with that just because trying to place these sensors in appropriate positions to see the flash and to not damage the connector when you're placing these. The loop sensors, that's the point sensors. For the loop sensors, when they're running them through the switchgear, I've seen where they get crimped down too tight, they can crack, and then you don't get the protection you're looking for. So they're not as robust as something like the bus protection, which is using CTs, which are very robust, or the zone interlock scheme, which again is using the CTs. There is some communication involved with it, but there is using the GOOSE messaging, you get a lot of speed out of this. So here's a question: how does using high overcurrent instead of bus differential is advantageous for arc flash protection? As we talked about in this one here, just high overcurrent is not as advantageous compared to the bus differential because you need to use time to coordinate it properly. The maintenance switch gives you some possibility to just really miscoordinate that and get some high-speed clearing, but then you do have the potential for human error and it not being put back into the proper running condition when maintenance crews leave. There's a question: how long does it take for the circuit breaker to open after the arc flash? So I said earlier, the circuit breakers are typically 3 to 5 milliseconds, can be a little bit slower. So that's where the bulk of your time is for any type of arc flash or fault event, is the opening of the circuit breaker. The reason where we're trying to work to try to minimize that incident energy is going to be on the detection and the command for the breaker to trip with a protective relay. Says you only talked about the bus faults. Can a feeder fault near the bus affect the equipment? So a feeder fault, what that's going to end up doing has the possibility of saturating your CT, and so it's going to require the differential to detect that or account for that so that it does not misoperate. The main circuit breaker for that one should be taking care of the fault on the feeder breaker. So the question is, for low impedance bus differential schemes, do they require dedicated CTs or can CTs be used as other relays? For the low impedance, they can be used with other relays. That's a benefit there. The high impedance, they have to be dedicated CTs. The low impedance, they can be shared. They can be different ratios, different classes. So very flexible. This question says, which is faster, 87? Oh, 87 bus high speed or low speed or low impedance differential? They're pretty much identical in speed. I guess if it came down to it, the high Z may be a millisecond faster, but the application for switchgear makes it really unapplicable because you do need the dedicated CTs. And there's other drawbacks to it too, where you can't do reconfigurable buses. It's kind of a stiff solution. Doesn't allow a lot of flexibility. The low impedance gives you a lot more flexibility and a lot more options because now you have access to the individual feeder currents. With the high Z method, you just have one summation current that's available for any type of information post-fault. The low impedance does give you a lot more information if there is a fault there. So there's a question: in the near future, only one box can have all the protection functions links with MUs. Yeah, we do have that for bus and feeder protection. So it's one box. It has all the bus bus protection, all the feeder protection, reclosing, sync check, everything's available in the one box. And as a protection engineer, I'd say you probably have at least 2 for redundancy. Yes, depending on the size of the station, you may have 3. That way you always have at least 2 relays. So if one of them goes down, you still have 3. The question based on a slide over here when I was doing the external and internal faults. The switch star for external is the blue star. So on the previous slide there where I had that, the blue slide is for the external. So this question says, typically an arc flash relay is located at the switchgear cabinet. Do you recommend having a separate device/relay for the traditional protection elements located away from the switchgear? So for arc flash relay, you need to have the sensor near where the arc flash is going to occur, so in the cubicle. So typically with the arc flash relays, it's a light sensor and it's on the relay that's protecting that element. So it is in that same cubicle. Depending on the space layout that you have, how long the runs are, because the optical sensors, they do have length limitations. You could have it in a different location. But again, if you move a relay like that, it's not just the light sensors being moved, it's also going to be the CT cables, all your control cables are going to be remotely located. The type of protection we're talking about here today wasn't so much dealing with light, it was more with just strictly current protection. The centralized protection we talked about at the end, using merging units, would just be a fiber going over there, so it could be remote. So it depends on your application, what you have. If you're doing something new where you can add that in, then it would make a lot of sense to do the centralized protection. If it's existing switchgear, then the standalone heated protection relay with arc flash is a valid option. We also do have things where you can add arc flash protection and say a transformer protection relay, and then take the arc flash sensors from that relay and route them, and if they see something, you trip the main on there. So it can give you some flexibility on that, with not having to upgrade all your feeder relays, just doing a transformer relay with arc flash protection and route those point sensors appropriately to give you that protection. So sort of depends. We can talk about that later. What does GE have for merging unit say to upgrade existing breaker cubicle, and does the merging unit control the breaker and read CTs, PTs? So we have the MU320E. This one can bring in currents and voltage information and alarms and contact outputs. So we can do trip, close, we can provide lockout functions, bring back alarms, and the currents and voltage signals. So that would be the MU320E. So why would you use arc flash protection and not just an overcurrent protection? Speed. That's the big thing here. So initially we talked about that our main goal is to minimize an incident energy. The overcurrent protection it's good protection. I mean, we've been using it for years, but it's not as fast as bus differential protection or the zone interlock protection, because you're doing coordination. So speed would be the answer there. One says, is there any that's international regulation for the minimum time for a switchgear to trip during a fault? Not that I'm aware of. I believe they're in that 3 to 5 cycle time range is typically what I've seen, and then when you're purchasing your breakers, you can specify what type of speed you're looking for, and higher speed is higher cost. It says, what are some of the downsides of centralized protection, and how can those be mitigated? I think the biggest thing on there is going to be the fact that it's new. being with the utility and stuff like that, I noticed there's a lot of resistance to change. So getting people to accept that there is a different way to do these things that's providing these additional benefits is a way to bring that in there. So it would be some training would be the biggest way to mitigate this, so people can get used to it. Because the thing that we have is that we have lots and lots of stations that are built the way they always have been. People get very comfortable with that. And as soon as you throw something new, there's just a natural resistance to that. But if we can do some training and show the benefits, then I think that helps with the acceptance. It says, do you mean 3 to 5 cycles, not milliseconds for breaker operation? I do. If I said milliseconds, I apologize. It is 3 to 5 cycles. This question says, which is faster, current monitoring with the light? Oh, current monitoring or light. So strictly monitoring for light is going to be faster because the first thing that happens when an arc flash occurs is going to be a large amount of light. Drawback with just looking for light, when arc flash sensors first came out, one of the big things that you heard about were people taking pictures of the new application, and the flash would trigger the arc flash and trip the bus. So you need to have it supervised with current at a minimum. Since the light is faster, arc flash light sensors are going to be a little bit quicker than the 87. It looks like about all the questions.
Okay. Well, thank you very much, Matthew, and thank you everyone for attending. We look forward to seeing you again at our next Tech Talk. This concludes today's webinar. Have a wonderful day.